Welcome back. So today we are going to address variation of parameters method. It is a little sophisticated, extremely helpful, as you will see, but it is kind of a little time consuming. It's worth it though, because it does what other methods couldn't do. So you may recall a linear ODE that is non-homogeneous. And for now, so far, we have used constant coefficients like this example, okay, 1, 1, negative 2. So that's one thing we have been doing over and over again. So we haven't used coefficients that are functions of t. I didn't write a subscript 2 of t here, just to make the problem a little easier. The other thing that we did not do is to choose a forcing function to be any function that is not a polynomial or exponential. The sine and cosine are also exponentials if you think about that. You may recall Euler's formula. So basically, we have only used polynomials and exponentials. You could say polynomials, exponentials, and sinusoidal, but sinusoidal are exponentials. So one of the drawback of the methods we've been using, like this one that I have here, which I'm going to go over very quickly, is that it doesn't handle non-constant coefficients well, and it doesn't handle functions like natural log of t or secant of t times square root of t, right? Non-polynomials, non-exponentials, they're a little difficult. So before we address this method, I'm going to work out a simple example. Please don't turn the page. I do want you to listen to this for two reasons. One is just quick review. It takes me a few seconds. But the other thing is, once we use the variation of parameter method, I want to make sure we get this solution boxed in green. Particularly this particular solution here. These are obvious. You could use any method and you'll get them very fast. But this one is at the heart of the matter when you use this variation of parameters method, okay? So the other thing I want to say before we start is, I call this part 1. I am going to work out an example and show you what steps you must take to solve an ODE like this one using this method. And I'm not going to show you yet why is it that it works the way it does. I feel like it would be a good idea to know how it works, understand the symbols, and feel comfortable and familiar with it first. And then in part 2, we're going to go through why it works the way it does, okay? So I will give you a couple of things to take for granted for the time being, okay? So if you remember, non-homogeneous like this with constant coefficients, the first step, we looked at the homogeneous piece. We wrote the auxiliary equation or the characteristic equation. You can call it whatever you want. We factor, we got 1 and negative 2, which means one of the solutions to this homogeneous is e to the t, and the other one is e to the negative t. And we call these basically the building blocks for the solution of this non-homogeneous equation. So by linearity, because this is a linear ODE, by linearity, the homogeneous piece is a multiple of y1 plus a multiple of y2. Recall that C1 and C2 are basically constants, okay? You might say, well, we know that. Why you have to mention it? Because with this method, things are going to change for you, okay? So of course, this C1 and C2 are just constants. And then we proceed to step 2, which is to try to guess a function that if I put it in here, I get an output called 4t. And of course, we're going to get a linear function, differentiate it twice. I'm looking for the particular solution. Set up your system. You know how to do this. And I got -1 minus 2t. Now, the entire purpose of this variation of parameters method is to get this particular solution, okay? That is the whole purpose, because these can be obtained very quickly. So make sure you focus on, understand that the focus is on this particular solution called YP, okay? This is YH. Okay, so let's get going. So what I did here is I basically rewrote my ODE, and I rewrote my two solutions. These are the built-in blocks, and you'll see why. It's not because of this linear combination, because that still gives me just the homogeneous piece. They are still the built-in blocks for this entire solution, okay? And here is how it works. What we want to do now is, instead of trying to guess a function that produces this polynomial, and we guessed this one, it took no more than a few seconds to get the particular solution. What we're going to do is we're going to say, based on these two solutions, which we know, one of them is e to the t and one of them is e to the negative t, can I get the particular solution by hitting y1 and y2 with some functions? Okay, so c1 and c2 of t are actual functions. So they could be, let's say, square root of t, y1, plus 1 over t, y2. That could be the solution, right? So that's why I wrote c1 of t and c2 of t, so you don't confuse it with this, okay? Now, I don't want to write c1 of t over and over and over again, so I'm just going to call them u1 and u2. So the bottom line is this. To find a particular solution, we need a linear combination of y1 and y2. y1 and y2 are known. We know them. Here they are. Basically, what we're going to need is u1 and u2. And this method is about how do you solve for u1 and u2. So before I proceed, I'm going to take you to page 5 first and then page 6. So we'll go to page 5 first. Pages 5 and 6. Okay? So page 5, don't be upset with me that I'm dealing with Algebra 1. You remember this from, I don't know, 8th grade or 3rd grade or whatever, system of equations, linear equations. And your teacher talks about 3 methods probably. The linear combination method, which is exactly what I did. I add them up, I get 2x equals 4, which means x equals 2. Plug in the 2 here, you get -1. So you get a pair, an ordered pair of solutions. You can use what we call the substitution method. And you can also graph those functions. So this is facing this way, this one is facing that way. You find the intersection, and that is basically a point. Now, some books would mention the 4th method called Kramer's rule, and it always upsets me when I see it, because Kramer's rule was not invented to solve a silly system of equations like this. It was actually created for a different purpose. Because if you use Kramer's rule on this one, it is so time-consuming when you could actually do this in your head, okay? So I don't know why some textbooks, basic elementary textbooks use Kramer's rule to teach Algebra 1 kids how to solve for x and y. That's not the purpose. The purpose actually comes in mostly in linear algebra and also ODEs like you will see today. But the way it works, in case you don't know, obviously we're looking for x and y. So it's a ratio of 2 determinants, and the determinants, the denominators for both is the same. And what are they? They're just the coefficients of x and y. Now, having basically written both systems like this, both equations like this, you have to use this standard form first. Let's call that A1, B1, C1, and A2, B2, C2. Okay? Once you write it in this form, then A1, B1, A2, B2 is what shows up in the denominators. So you have 1, 1, 1, negative 1, here they are. And determinants of the denominator is just negative 1 minus 1, which is negative 2. Okay? So that's easy. However, the top is different. So when you're looking for x, look in here. The first column deals with x, and the second column deals with y. So when you're solving for x, instead of writing 1, 1, you actually write the outputs first. And for y, for the y column, you actually write the coefficients of y, 1 and negative 1. Here they are. And then you find determinants. It's negative 1 minus 3, which is negative 4. And that's why we got 2. Same thing here for y. In the place of y, you don't write 1 and negative 1, but you actually write the output. And in the place of x, you write x, the coefficients of x, 1, 1. Okay, 3 minus 1 is 2. 2 over negative 2 is negative 1. And once again, we got 2 comma negative 1. Okay? So why is this helpful? Well, it is extremely helpful in trying to solve for U1 and U2. I'm going to go back to page 6 now. I'm going to throw a system at you. You could probably tell that this system is coming definitely from the ODE that is given to me and some other things. For now, I just want you to take this for granted, okay? We'll prove it next time, okay? I just want to make sure you know how to work with this and then and get familiar with the method, solve problems using the variation of parameters, and then we'll talk about where is this coming from. Notice that my so-called variables are, I'll put them in green, are U1 prime and U2 prime. Notice we're looking for U1 and U2. Y1 and Y2 are known. I know they're not constant, but they're known. We're not looking for Y1 and Y2. We're looking for U1 and U2. However, this system on the last page, does not have U1 and U2. And there is a reason why U1 and U2 disappear completely. They are actually functions of U1 prime and U2 prime, okay? So my so-called variables, what I'm looking for are U1 prime and U2 prime. And once we find U1 prime and U2 prime, it's not going to be difficult to solve for U1 and U2, right? If you know the derivatives, you know U1 and U2. You just integrate. All right. So we are going to proceed the same way we proceeded here. Okay. So U1 prime, let's begin with the denominators. It's just Y1, Y1 prime, Y2, Y2 prime. Here they are. And determinant of that is in the denominator, and we're going to call it W. We're going to call this W2. We're going to call this W1. W stands for the Wronskian, famous mathematician. So that's why we call them W's. They could be numbers, right? As we did here. It's just number. These are numbers. But they can also be functions, like in our case. So R of t is the Forcian function. And y1 and y2, remember, are functions, these. So the Wronskian, in this case, are functions. And the way we handle the top, U1 prime is in the first column. So instead of writing y1 and y1 prime, we write 0 and R of t, just like I did here, okay? Just like I did here. And in the place of and in the second column, you literally copy the coefficients. The same thing here. To find u2 prime, instead of writing y2 and y2 prime in the second column, you actually write the output 0 and r of t. And for the first column, you write y1 and y1 prime. So once we find this Wronskian and find these determinants and solve for u1 prime and u2 prime, we can integrate u1 prime and we can integrate u2 prime, and we will be all set. We would plug in u1 here, and we would plug in u2 here. We already know y1, we already know y2. Everything is simple, and we should be able to find my particular solution. Again, you might say, why are you doing all of this when you can do it so fast from here to here? It's because this is an easy one. And if I have a much harder one, this method would not work. So we had to resort to the variation of parameters. So what is the Wronskian? If you go back here, the Wronskian is this, isn't it true? And the top is this, and the top for u2 prime is this. So I have to remember 0 r of t, y2 prime. 0 r of t, y2 prime. Here is y2. Differentiate y2, you get y2 prime. The Wronskian is just y1, e of t, e to the t, y2, e to the negative 2t, and then their derivatives. Derivative of this is this, and derivative of this is this. And finally, w2, let me write this quickly. Here is w1, and w2 is y1 prime, and then the outputs. y1 prime, derivative of this is this, and then the output 0 and 4t. 0 was there, and r of t, which is 4t. 4t is your r of t. 0 r of t. Okay, so you just find determinants. So for the Wronskian is this minus this, you get this minus that. I cleaned it up, and I got this. I'm going to write it in blue. This is the Wronskian. Okay. And this is W1. W1. And this is W2. And then we're going to find u1 prime and u2 prime. Okay, so for w1, 0 minus this, that's going to give me 4t e to the negative 2t. And for w2, you get 4t e to the t minus 0. Okay, so you should be clear on anything that is in blue. Okay, then we go to u1 prime and u2 prime. Go back to page 6. u1 prime is w1 over w, and u2 prime is w2 over w. So you just push your pencil, this divided by that. Here it is. I cleaned up the mess here. You multiply by negative reciprocal. No, sorry. E to the negative t at the bottom becomes e to the t at the top. So you get e to the negative t, and there is a t sitting there, and the negatives cancel. And then for u2 prime, you get w2, which is 4t e to the t divided by negative 3 e to the negative t. I got negative 4/3 t e to the 2t, and I'm also going to circle these. So this is u1 prime, and this is u2 prime. Okay, so I got w and w1 and w2 just so I can find u1 prime and u2 prime. And once I know u1 prime and u2 prime, I can find u1 and u2. And once I find u1 and u2, I do this linear combination, and I should be done. So obviously, what do you think we're going to do now? Of course, we're going to integrate. So I just summarized all of our foundings. Here is my y1, my y2, my building blocks. Here is my w1, my w2, and my w, the Wronskian here. And here is u1 prime, and here is u2 prime. Basically, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, I just copied them here. So in order to find u1, we're going to integrate u1 prime. I pulled out the 4/3. I used, what is it called? My goodness. Integration by parts, okay? I used f and g. So I called ft, and therefore f prime is 1. And I call this g prime. And therefore the integral of e to the negative 2 is this. And this is exactly fg minus the integral of this. Let me, I don't know if you know this. I'll write this for you, okay? The integration by parts really came from the product rule. I don't know if you know it. So f prime g is f prime g plus fg prime. Therefore, f prime g, this piece here, is just this minus that, right? So it's just fg, the whole thing prime, minus fg prime. And therefore, if I integrate all sides, I get the integral of this equals the integral of this. Well, antiderivative with derivative cancels. You just get fg. You get fg minus the integral of fg prime. Isn't that the integration by parts? Okay? It really came from the product rule. So that's all I'm doing here. So I call this f, and I call this g prime. I solved for this basically. fg prime is this minus that. Same thing, okay? So I got 4/3, and then fg with no integral, fg minus the integral of this, and so I got, that's just a plus, but then the integral of e to negative 2t is negative e to negative t, and so that's my u1. And it looks ugly, but you'll be surprised something's going to happen. Because remember, we're going to multiply u1 by y1. And when we find u2, we're going to multiply it by y2, okay? So don't lose hope here. Things are going to get nice. The same thing for u2. It's negative 4/3 times the integral of t e to the 2t, dt, of course. Integration by parts again. I call this f, and I call this g prime, because exponentials remain exponentials, but I would rather differentiate t to make it 1, okay? And I used integration by parts. I got this, and the integral of e to the 2t, this is obvious, this is obvious, this is obvious, is 1/2 e to the 2t, right? And 1/2 times 1/2 is 1/4. And then I foiled. I didn't foil here, but I did foil here because those constants are different. I got negative 2/3 t e to the 2t plus 1/3 e to the 2t. So I found my u1 and my u2. Okay? So now, my particular solution is this u1 that I just found times the building block plus a u2. Remember, we used to call these constants for the homogeneous piece, but this is not what we're doing. We're doing something completely different, okay? Completely different. So u1 from the previous page times the first block, y1, plus u2 times y2. And notice what cancels. That cancels, that cancels. You're left with negative t times 4/3. And then that is minus 1 times 4/3. 4/3 times negative 1. Here it is. So this whole thing is just this. Okay, same thing here. That cancels with that piece, and that cancels with that piece. You get negative 2/3 t plus 1/3. Negative 4/3 plus minus 2/3 is negative 6/3, which is negative 2 t. Minus 4/3 plus 1/3 is negative 3/3, which is negative 1. And isn't that what I got earlier? Okay. And therefore, my solution is the homogeneous piece we got earlier. These are actual constants, real numbers. And this came from here. Okay. That is essentially the method of variation of parameters. We still don't know where this is coming from. We still don't know where did the U1 and U2 go. I don't see them here. I do expect R of t. I do expect Y1 and Y2. Where are these derivatives coming from? And where are the U's, the U1s and U2? So I hope you were able to follow how to proceed with variation of parameters. I know it's a lot longer than doing this, but trust me, when we have a function with non-constant coefficients, or if we have a forcing function that is not the typical polynomial or exponential, this method will save you, okay? So hopefully this makes sense. Thank you for listening.